we talk about scientific measurement, we talk about the concepts of accuracy and precision, and they are different. Accuracy is getting the correct answer. So if you're bow hunting, accuracy is your ability to hit the center of the target, to hit the bullseye, get your arrow where you want it. If you are given a balance and an object, and you measure that object, and the mass that you get for it is the actual true mass of the object, that's an accurate measurement. That's different than a precision measurement. If you're bow hunting, and you've got your target, and you've got your arrow, and boy, you're nowhere near bullseye, but you can split your first arrow with your second arrow, that's precision shooting. If I give you a balance and an object, and you measure that object 40 times, and every single time you get the same answer, that's a precision set of measurements. Now, they may not be the correct value. The object might have a mass of 55 grams, and you're getting 32 grams every single time, 32.0 grams, a bunch of times. It's precision measurement. The goal, of course, is to be both accurate and precise. Now, when I talk about the problems we have with the balances in here, when you do a lab, you want to make sure you get the same balance every time, because these balances are precision instruments. If I give you an object and a balance, and Josh measures the same thing 3 times, with those balances, you will probably get the same mass 3 times. However, if I hand him 3 different balances and the same object, I can pretty much guarantee you're going to get 3 different masses no matter how careful you are. You can, with the same balance, you can get the same number again and again and again. The instruments are precision. However, I have found that none of them are very accurate, unfortunately. That's the difference between accuracy and precision. Now, when we talk about precision, I'm going to hand you all, rulers, and I would like you all to measure the width, the width of your textbook. Of course, we use centimeters in here, and jot that number down someplace. Okay, measure the width of your textbook. Oh, we have an extra of the nicer board. Yeah. They have the little crappy ones. It's going to be hard. That's okay. Okay. Do your best. Okay, measure the width of your textbook. Somebody give me a measurement. What do you have? Josh, what do you have?
20.1 centimeters.
Okay, we have 20.1 centimeters. Give me another measurements. Okay, somebody has 20.6 centimeters. You have 20.3 centimeters. 20.2 centimeters. Earlier when I did this, I got 19.6 centimeters. Okay, we're going to use yours. 19.4 centimeters. Okay, that's plenty. That's plenty. Now, these are all wrong. Well, I should say, I don't actually know how accurate they all are, but none of them are as precise as they could be. So if you would be so kind as to look carefully at that measuring device in your hand, the smallest marks you see on the metric side of the scale, so the numbers that you see, 1, 2, 3, 4, 5, etc., those each indicate a centimeter, correct? Okay, and we can put one of these up here for the benefit of the people viewing at home. So those numbers are centimeters. Now if we go to the little mark just past the 2, the first little mark, what is that? 2.1 centimeters, close to 1 millimeter. Okay. If you took a measurement and it was directly on that mark, then it's 2.1, and it's not past that mark at all. It's actually 2.10. Because you can go one digit further than the last marking on your instrument. So the example we'll use with this, I'm going to move this a little bit. If we have a ruler that's only marked in centimeters, and it does not have millimeter marks. If we have something that lands there, can we say with some level of certainty that that's 1.25 centimeters or even 1.2 centimeters? Sorry, you're not that good. You don't have calipers in your eyeballs. We can say it's more than 1 centimeter or less than 2. So when this is called our uncertainty digit. When we record that, we don't want to record 1 centimeter because that's not true. We want to record 1.5 centimeters. If something ended up with a measurement that was right there, we would want to record, well, it's not actually precisely on the 2, but it's sure not 2.5 or 1.5. We would record that as 2.0. We can go one digit beyond the last marked digit on the scale you're using. That's an uncertainty digit. That's always going to be a 0 or a 5. So, if these measurements for your textbooks were all spot on, then that's 20.60, 20.30, 20.20, 19.40. If they're a little bit beyond that millimeter mark, then it might be 20.15, 20.65. Go ahead and measure it again. See if you get the same thing with that in mind. And you may. And I'll measure the one I've got here. Okay, you say it's a little bit between? If it's a little bit between, then, so which measurement was yours, Clyde? 20.6. So you would say that's 20.65? Okay. That's about precision. That last digit tells us how much of a precision measurement, the scale that was used to get the measurement, allowed us to record. So, now we're going to talk about how we keep track of that precision. So you made a measurement. You know how precise your measurement was. That's wonderful. But when you pass those measurements on to somebody else, how do they know how precise the tool used to make the measurements was? Significant figures. So when you make a measurement, you're going to record those digits as sig figs. We're talking about that in a second. First, let's talk briefly about calculating error. And if you can pass all of the meter sticks up into this corner and get them back at the ruler back in this corner and get the box. So percent error is very similar to what we did when we calculated percent loss. Okay? You're taking the accepted value, that's the true value that we all agree on, subtracting it from whatever you got as an answer, and then dividing it by the true value, multiplying by 100. When you did this as percent loss, if you had, so first of all, let's do percent error. Imagining that you're measuring the density of water. What is the density of water? 1. Very easy to remember. Just 1. So you're measuring, well, we're going to say that the density of water is 1.0 grams per cubic centimeter. If you're measuring the density of water and you get numbers that give you a value, this is your experimental value, of 0.96 grams per cubic centimeter, do you have a completely accurate answer? No. Well, we want to figure out what your percent error is. By what percent are you off? What do? We take the accepted value, which is 1.0, subtract the experimental value, which is 0.96, and divide it by the accepted value, which is 1. Multiply the whole thing by 100. So go ahead and do that computation. Get the calculators out, I'm sure. What is your percent error? I have a vote for 4% error. Anybody agree? Okay, 4% error. Not too bad. Not terrible. Not, you know, jump up and shout for a party grace, but not bad. That's a positive percent error. That means your accepted value is less than experimental. How does that mesh with what you remember from calculating percent loss? If you lost material, you had a positive percent loss, right? Okay. What if we went the other direction, and when you measured this, you got an experimental value for the density of water of 1.15 grams per cubic centimeter. So now we have 1.0 minus 1.15 divided by 1, the whole thing, times 100. What is your percent error now? Negative 15%. Pretty crazy. But it's also your experimental value was greater than the accepted value. So this is like if you made material during your lab, then you had a negative percent loss. Okay? So that's pretty easy. All right. Let's start to talk now about sig figs. This is where we say you have all the digits that you know with certainty plus 1. So you've practiced that. We're going to talk about the rules for what becomes significant. Okay, you have this in your notes. All non-zeros are significant. Zeros have got some special rules. In your notes, I'm going to stop this video. We're going to go up front and we're going to do some practice with these.